One last thing I wanted to mention about the gravitational force is the concept of weight. So this is mostly just a little bit of terminology to be aware of. So first of all, what do we mean when we say weight? Weight definitely is not the same as mass, right off the top. So those are two distinct terms. The meaning of weight is that it's basically the gravitational force acting on an object. So if you're ever asked to calculate the weight of an object, or if you're ever given the weight of an object, that's the same thing as saying the gravitational force on the object. So for our purposes, it's really just the mass times 9.8. So that's why sometimes people use in everyday life weight and mass interchangeably. They're not the same thing, but under normal conditions, really the weight is just basically the mass times a certain number. So they're proportional to each other. And sort of conceptually, you know, there's sort of just a conversion factor between them. But in reality, they actually mean quite different things, because mass is the amount of inertia that an object has, whereas weight is an actual force that's acting on an object. So that's the first thing to say off the top. Weight just means the force of gravity. There's another concept, though, that's a little bit more confusing. It's called apparent weight. Apparent weight is basically how heavy an object feels if you are holding it. And this is sometimes equal to the object weight, but sometimes it's not equal to the object's weight. So let me explain. Suppose that you have an object like this and you hold it like that. Let's analyze this situation for a second. If we want to analyze something in this class, we start with the free body diagram. Okay, so let's say here's this box that I'm holding. We know that there's a gravitational force pulling the object down, and we know that this gravitational force has a magnitude mg. But also, and this is something we'll talk about in more detail later, and I'll give you the proper terminology to talk about this and everything like that. But basically, my hand is holding the object upward so that it doesn't fall through my hand. The reason why it doesn't have any acceleration right now is because the force of gravity is being balanced out by an upward force that my hand is exerting on the box. And I'm not going to worry about the nature of this force just yet. I'm just going to generically call it, let's say, F up, because it's an upward force. Okay. So F up is basically what we think of as being the apparent weight of the box. So F up is the apparent weight. Why is it the apparent weight? Again, because if I'm holding this box, what I actually feel is not the object's weight. What I actually feel is the Newton's third law reaction to the force that I'm exerting on the box to hold it up. And in fact, this is what's measured on most scales, is not the object's weight, it's the force that the object is exerting on the scale. So like, for instance, if I draw my hand here, there's a Newton's third law reaction to F up, which is a downward force. So this oval here represents my hand. That Newton's third law reaction of the box pushing down on my hand, that's actually what I can feel when I hold the box. And if I add some weight to this and make it even heavier, it feels like my hand is getting pushed down even more. And that's because I have to exert an even stronger force on this stuff to hold it up. Okay. Now, what is the actual value of F up is the next question. So Under normal circumstances, so under normal circumstances, you have the acceleration of the box equals 0. So I write F up minus mg equals ma, which is 0, which means that F up equals mg. And I end up getting, not surprisingly, that the object's apparent weight is equal to the object's weight. And everything makes perfect sense. And that's how a scale works. That's how a scale works. Because normally the apparent weight is just equal to the weight. So the reading on the scale will equal the weight of the object that's on the scale. That's under normal circumstances, okay? Now, what do I mean by normal circumstances? What are abnormal circumstances? Well, suppose, for instance, I take this box and I jerk my hand up suddenly like that. So, grab a heavy object around you and try that. Move your hand up, not just move your hand up, but jerk it up very suddenly. And what you'll feel is that it feels like for a moment, the object is heavier. And conversely, if you drop your hand suddenly, it will feel momentarily like the object is lighter. So for a few moments there, the object's weight is not equal to its weight. And that's because the object is accelerating. In this case, you have acceleration not equal to 0. So the same F equals ma equation applies. But this time we cannot plug in acceleration equals 0. So we get an apparent weight equal to mg plus ma. And that was under the assumption here. Notice that in this equation here, I assumed that the acceleration was pointing upward because I made ma is positive. The acceleration is in the same direction as F up, so that would be an upward acceleration. I got an apparent weight that's higher than mg because it's mg plus an extra piece. Conversely, if the acceleration is down, you'll have F up minus mg equals negative ma, because a is pointed downwards, and if a is pointed downwards, you have to make a as negative. So this would be for an acceleration down. And this would give you F up is mg minus ma. So the object's apparent weight would be less than its real weight. So the apparent weight could be equal to, greater than, or less than the real weight of the object, depending on how the object is moving. So this is what causes, like if you're in an elevator and like the elevator starts accelerating upwards, you'll feel like momentarily you get pushed down a little bit. That's apparent weight. If you're on a roller coaster, the sensation you experience when you go up and down on the dips and rises of a roller coaster, that's apparent weight. Even weightlessness on like the International Space Station is caused by apparent weight, for reasons that we're not going to get into because that involves talking about a lot of details about orbits and things like that. But basically, things can appear weightless if the acceleration of the object is negative g. So consider this last case here. What if, consider that last case there, what if the acceleration is g pointed downward? In this case, if you plug that in, you'll get that the apparent weight is mg minus mg equals 0. So the object has apparent weight 0. What does that mean? That is what we think of as being weightlessness. That's what we normally call weightlessness. Weightlessness is actually not necessarily the absence of weight. It's actually the absence of apparent weight, usually because something is in an environment where it's falling so fast that it looks like things are floating around. Like if my whole environment that I'm shooting this video in was dropped from an airplane and, you know, falling at an acceleration of g, and I released this pen in front of me, it would just float in front of me as if it was weightless, because it would be falling at the same rate that I'm falling and at the same rate that everything in the background of the video is falling. So then everything seems to kind of hover and look like it's not getting pulled down by gravity. It actually is getting pulled down by gravity, but it's just kind of a trick of the environment. So I'm not going to dwell on this at all. This is not the main focus of our course, but I want to at least mention this terminology. So weight is the gravitational force. Apparent weight is the force required to hold something up. And that includes, by the way, if you're interested in the human body, that includes like our muscles and bones have to constantly hold our body up. So that includes that force that you experience as your own body's weight, because you have to hold yourself up. So this can affect kind of the sensation of how it feels to hold up your own body as well. So that's apparent weight, the sensation of how much force it takes to hold something up against gravity. And weightlessness is when the apparent weight goes to zero. It's not when the weight goes to zero. So those are the little terminology pieces there.